Hello, pre-calculus students. This is Mr. Bean. Let's review our unit on function analysis. Here's the 3 lessons that we had, just as a quick reminder. Those are the 3 things I'm going to go over real quick. This is not to follow the review that I've made there on the website. It's just to give you a quick review of what these concepts were and just the skills portion of it. So let me remind you something, and that hopefully will make this a little bit clear for you. When you're looking for the domain, actually, let's talk about discontinuities first. If you're looking for the discontinuities, it's because you have a fraction that is 0. That is when you have a discontinuity, okay? If your fraction ever equals 0. In other words, no matter what your fraction is, anything that's on bottom, blah, 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 times blah, blah, minus another, minus some blah, blah, blah stuff, you take the whole thing and just say equals 0 and solve it, because that's where you'd have discontinuities. All right, and then if you have a radical does not create discontinuities. Let's make sure you understand that. This does not create a discontinuity, but it does create a restriction on the domain. So if I had x minus 3 here, then you'd say that it has to be greater than or equal to 0. Solve it, you get x is greater than or equal to 3. That's not a discontinuity. It's just what the domain is. It has to be greater than or equal to 3. And we say it's continuous on its domain unless there was a 0 in a denominator. Okay, so let's do some examples of that. So you could write these down if you want, or you just watch me, however you're working through this. This one, you just say greater than whatever underneath the radical. You say greater than or equal to 0. Solve this thing, greater than or equal to negative 15. I'm dividing by 5, so I leave the sign the same. Even though that's a negative 15, does not matter. It's what you're dividing or multiplying by. And this was positive, so x is greater than or equal to negative 3. That is the domain of this thing. Now, if it also said to classify the discontinuities, that's the word I'm looking for here, is what type of discontinuity is this? Well, there is no discontinuities. It is continuous on its domain. And that is the entire answer. That is the domain and its classification, the type of discontinuities there are. There are none. That's what this means. All right, let's try this one. You have a denominator, so we set the entire denominator equal to 0 and solve it because it can't be that. But you can also say that what's underneath the radical, it has to be greater than or equal to 0, and in this case we drop off the or equal to because the entire denominator here is the radical. Solve that, we get 3t greater than 10, so t is greater than 10 thirds, and then we also have the statement, if we want to say where are the discontinuities, we say it is continuous on its domain. I'll abbreviate here just for sake of running out of space. Okay, same thing as the last one. All right, now here, ooh, this is tricky. So again, we're going to take the entire denominator, set it equal to 0, and solve that. That means you have to say that x equals 0, or, so I took care of this first piece, but we're multiplying, or you have the second piece, 56 minus 4x can't equal 0, but we're actually going to use an inequality. We're going to say that it's greater than 0 because it is a radical there. So now what do we do here? Well, we already know that x cannot equal 0, so let's say it cannot equal 0. And then when we solve this, when we divide, we're going to subtract 56, divide by a negative 4, so that changes that sign. Let's see, 40 is 10, another 16 is 4, so 14. X is less than 14. So we have x is less than 14, and x cannot equal 0, so here's part of the domain there. Here's the other part of the domain, but then we also need to say that this here is a whole. It is a removable discontinuity because that's canceling. So that is a whole at x equals 0, but it is still a discontinuity. So all of these things are all the answer here. All right, last one. We take the entire denominator and say that it equals 0 and solve it. So if we subtract 2 from both sides, you'd get a negative square root of w equals negative 2. Get rid of the negatives, square both sides, and you get w equals 4. So we know that w cannot equal 4 because that would make this, if you think about it, plug it in. 4, square root of 4 is 2. 2 minus 2 doesn't work. So that cannot be in the domain. We also have to think about the radical. So the next step is take whatever your radical is and say that it is greater than or equal to 0. Here's where I have a lot of students say, whoa, whoa, you can't say that it equals 0 because this is in the denominator. No, it's all right here, because if this is a 0, does that make the entire denominator a 0? No. It's only if the entire denominator would be a 0. It can't equal 0. So w is greater than or equal to 0, and it cannot equal 4, and this one is a vertical asymptote. That one right there is a vertical asymptote. So, or in other words, a non-removable. It does not remove. There's our domain and what type of discontinuity it is. Let's do one more of these just to kind of make sure I've covered all the bases that you might be struggling with. If I factor this entire thing, it would come out to be, I'd take out a 2. Here, let's factor this thing. It becomes a 2t times t plus 1. What do we have here? This one we have t, both have to be minus. Yep, both are subtraction. How do I get to 24? 8 and 3. So minus 8, minus 3. All right, what cancels? The only thing that cancels is this and this. Those t's are going to cancel, so that's the one where we have a hole. So the domain is all real numbers except for t cannot equal 0, it cannot equal 8, and it cannot equal a 3. Those things would make a 0 on the bottom. The negative 1 does not matter. That's numerator, so we ignore it completely. And then we say that this one, I'll change colors here, this one, whoops, is a hole, and the 0 is, I should point that to the 0. And then the 8 and the 3 are vertical asymptotes. In other words, this is removable because it canceled, and these are non-removable at the 3 and the 8. All right, lesson 2 now. We will graph this thing. So let me put my calculator and plug that in, see what we get. Okay, I've plugged this thing in, and if we take a look at the graph of it, this is what it looks like. So one of the things that's pretty hard to see is that it looks like the graph just stops right here at this point, but it actually keeps going down because you have to think through what would the domain be. So that we can use a calculator to help us, but we also just need to kind of think through let me pull this over. I'm going to leave that here so I can have it to refer to. But we also have to think about what just the domain is normally from what we've learned in the past. So I know that there's no restriction here, there's no restriction here, but this is where I have a restriction. X plus 5 has to be greater than or equal to 0. So x has to be greater than or equal to negative 5. That means this graph, 1, 2, 3, 4, 5, it actually, if we trace it, you could see it's got to come all the way to 5. If I hit trace and I go over here, actually let's just plug in negative 5 now. And it jumps, negative 5, 0. And so what you have, pull that one over as well. So what you have is this is actually on the graph. You just can't see it, that it is supposed to connect here, whoops, all the way down. There's just not enough pixels on the graph, so there it connects. All right, so our domain is, what is our domain? All of the x values from negative 5 until we get to infinity. It just keeps going and going. And, oh, I could put a bracket there because it includes negative 5. The absolute max or min of this thing is, there is no absolute max because it goes forever and ever here, but there is an absolute min. So there is an absolute min, and then now we have to figure out what the y value is. Remember, when it says the value, we're just talking about a y value. So let's see. Second, calculate. The minimum is option number 3, and then I go left boundary. Now what I like to do is just hit negative 1. If I hit negative 1, hit enter, that'll give me my left boundary there. Go over here, just instead of scrolling right, I could just hit the number 1, and that sets my right boundary there. Hit enter, and my minimum value is negative 2.2. So absolute min at negative 2.24, let's go 3 decimals to be safe, 247. And then my extrema. So I have a relative, this is going to be tough to squeeze all this in, a relative min at the endpoint here at negative 5, 0. So there's a relative min at negative 5 and 0. Oh, sorry, pin's hard to control. And there is we already did the absolute min, so it's at 0.097, and there we could write that one down again for the coordinate point. But there's also this right here, that is a relative max. So we have a relative max, and then you just need to do second calculate and find that coordinate point. That's how you do this. Let's sketch this graph too while we're at it. 1, 2, 3, 4, 5. I know there's a closed interval. Let's see, the minimum we said was, or the absolute min was at 0.0912, about there, and then it just kind of goes off forever. And then so after we'd find that maximum point, it'd be somewhere around there. Increasing. It is increasing from negative 5 up until whatever this x value is. And then it's increasing also, oh, I wrote way too big. It's increasing also from 0.097 up until infinity for increasing up like that. Decreasing, it's only decreasing from one x value, one interval, from that x value to that x value. So there's just one answer there. And end behavior. Let's get rid of that stuff. Get out of the way. End behavior on the left side, there is no end behavior on the left because the graph doesn't go forever. So we can kind of say that it's, whoa, that's cool, black. We can just say that it's not applicable. It doesn't apply for that problem. But on the right side, it goes up forever. All right, that's basically lesson 2 in a nutshell. Lesson 3, piecewise functions. What did we do here? We're plugging in numbers. So the big trick is you have to recognize what letter it is. So I'm not going to do all of these, but I'll plug in like h of negative 7. Well, if I do h of negative 7, that's this equation because it's h. Now I got to look here. Which one is negative 7? It's this piece. So I plug a negative 7 in to, and then I just put parentheses, negative 7 squared minus 4 times negative 7 plus 8, that's a negative 7, negative 49, negative 7 squared is 49, negative still in front, plus 28 plus 8, and then you just kind of write in whatever that simplifies to. Okay, that's evaluating, just plugging the numbers in. Pretty basic there. These graphs are a little bit trickier. So let's graph 3 halves x plus 2. We come up here to 2, 1, 2, 3 over 2. There, 1, 2, 3 over 2. Okay, so there's a line. But the problem is I don't want, 1, 2, 3 over 2. I don't want that whole line. We only want where x is less than negative 1. So that means all of that we would erase. And so we're only caring about this open circle right there. Okay, next one, x squared minus 5. What does that graph look like? 1, 2, 3, 4, 5. There's the vertex. And it's going to go up and up. Now I know it's not going to go past this because it would be failing a vertical line test. And here the x's are between negative 1 and 3. Let's go over 1, 2, 3, over 1, 2, 3, 4, 5. So we're going from 1, 2, 3 here. This one's open. And the other one is closed. So there's my parabola. Something like that. And then the vertical, what is going on here? Absolute value. So it's, let's see, 1, 2, 3, 4, up 1, and it opens down. Going like this. That one is also open right there on that spot. Okay, there's your graph. So you're trying to think about what the entire graph would look like and erase the part that you do not need. Okay, and the last thing we're doing is we're going to check and see if this thing is continuous or not. Is it continuous? The way we figure that out is we're going to take the first piece, 7 minus x, and see if it equals the second piece. They have to have the exact same y value. If they have the same y value, then we're good. So at what x value are we checking that? It is at negative 4. This is how you show your work on this. So make sure you're showing work. Plus 21. And then we evaluate this. 7 plus 4, that's 11. Here we have a negative 12. Did I do that right? 7 plus 4 is 11. Here we have a negative 12. We're adding 21, and that's a 9. So this is not continuous. That's how we show it. Okay, that's it for the whole unit in a nutshell. We kind of did that pretty quick. Good luck on that test, and I'll see you back in a couple units.